In this particular tutorial, we will try to understand the graphical transformation of a function. So suppose if we have a function, let's say fx, and we want its transformation to the modulus of fx. So what will change in the diagram or in the graph or in the plot of a function once we change it from fx to the modulus of fx, or the absolute? This sign denotes whatever is written out here. This sign denotes the absolute value, or we can say modulus. Okay, so all right, so suppose if I have a function, let us suppose as y is equal to x, comparing it with a straight line equation, y is equal to mx plus c. We have y is equal to x. So once we compare, we get the value. We can write it as this. Suppose if I have a function as this, y is equal to x, so I can always write it in the form of y is equal to 1 multiplied by x plus 0, where this value is what? M. This value is what? C. C is nothing but the y-intercept. So we know from our understanding of the plotting of straight lines that y is equal to x is nothing but a line that passes through the origin, that is 0, 0, and which makes an angle of 45 degree. Why 45 degree? Because the value of m is 1, and we know the slope of the straight line is m is equal to tan theta, and if the value of 1 is equal to tan theta, then the value of theta is equal to 45 degrees. So this is our f of x, where f of x is x. We can write it as y is equal to x, or we can write it as fx is equal to x. It's just the same thing. To represent a function, we always use the notation. We always use the notation as y is equal to fx. All right. So if the function, this is a function of y in terms of x. All right. So this is denoted as y is equal to fx. For now, if the function is on x y plane in the rectangular coordinate system, this is rectangular coordinate system wherein I have two straight lines cutting each other perpendicularly. So y, this is a plot on the yx plane. This is a plot on yx plane. Alright, so the function will be y is equal to fx. So as the value of x changes, correspondingly y will change. So the value of y, or the y, is dependent on x. So this is a function of y in terms of x. Okay, so now moving to the other part. So if I have to change it from, let us suppose this was written as y is equal to x, and I will change it to y is equal to modulus of x. So remember the rule, whenever fx changes to mod of fx, mirror is x-axis and all the values of y are okay. So all the values of y are positive. That is, where all I was getting y as negative, this will all change to positive, from negativity to positivity. Okay. So with this modulus function, so suppose if I have a rectangular coordinate system, and in it I have a curve as this. So treating x-axis as the mirror, so we will have the whatever lies below x-axis, that is in third and fourth quadrant, is reflected through x-axis and first and second quadrant. So whatever is the this is what this is third quadrant, this is fourth quadrant. There is nothing in fourth quadrant. There was some part of this function. Let us suppose this function was gx. There was some part below the x-axis, this part that was below the x-axis in the third quadrant. So it has to be reflected through, this is mirror, this is mirror, this is x-axis, this is mirror. We have taken its image, this is image which is in the second quadrant. So now what we will do is we will just erase it. Okay, so we will selectively erase it. Okay, so we will forget this part, and this part will transform to, this graph will transform to, this graph will transform to okay, so whatever part was below x-axis, we have just taken its mirror image on, the x-axis. The x-axis is treated as mirror, and whatever part was there in the third quadrant, this is reflected through x-axis in the second quadrant. And imagine if there would have been any part in the fourth quadrant, it would have reflected through x-axis in the first quadrant. So in picture 1, this was the plot of gx, and in the picture 2, this is the plot of modulus of gx. There is nothing below x-axis. Everything is, now you can say that whatever be the value of x, 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 y will continue being positive. Correspondingly, y will have all positive values. Initially, what we suppose, if I had some x here, the y would have been, this would have fetched as some negative value. This would have got us some negative value. But now, since we have taken the absolute value of gx and or the modulus value, whatever be x, y will continue being positive. Whatever be x, y will continue being positive. X be negative or positive, y will always be positive. So this was the graphical transformation of a function. Let us suppose that if it is gx, fx, hx or whatever to modulus value. Suppose if I have some function hx is equal to sin x. So ordinarily what sin x looks like is this. Okay, so what it looks like is this. Looks like this. It's a sinusoidal curve alternating values in between -1 and +1. Sin x is a bounded function. The values keep oscillating between +1 and -1. So this is the plot, and this continues all the way to left and right. It continues due to paucity of space. I am not stretching it any further. Okay, let me draw one more curve. Okay, I think this is sufficient. Okay, so it goes till eternity, till infinity. It stretches both left ways and right ways. Due to paucity of space, this is not practically possible to continue drawing it, but for our understanding, this portion is enough. So now if we transform hx to modulus of hx, that is, we have transformed sin x to modulus of sin x. So whatever portion is, suppose first step is what? First things first. X axis is acts as mirror. Reflect whatever is in third and fourth quadrant to second and first quadrant respectively. Okay, and all y will be positive now. Erase everything below x-axis. So we have to reflect whatever is there in the, so the reflection of this part, will be this, the reflection of this part will be this, reflection of this part will be this, reflection of this part will be, and the reflection of this part through x-axis. So whatever is there in the third and fourth quadrant is reflected back to second and first quadrant through x-axis, and x-axis acts as mirror. And now whatever is there in the third and fourth quadrant, we will just erase it. Erase it. So now we are left with the graph of modulus of sin x. This is the graph of modulus of sin x. So earlier we had was sin x, and now we have mod of sin x, and the values of mod of sin x will keep oscillating. This will keep oscillating in between. It will keep oscillating in between 0 and 1. At max it can attain 1, and at the lowest it can attain 0. It will not go beyond 0, and it will not get below 0, and it will not get beyond 1. So this is the region we have got of modulus of sin x. And one thing more important to note here is this, that this is a bounded function, and this is symmetrical about x-axis. One thing more, that in functions, in transformations of mod of fx, in such transformations, the graph is always, in transformations from, let us suppose if I had a function gx that transform to mod of gx. Okay, not always, but graph is symmetrical in case of sin x, cos x. Okay, so this is the homework for you, that now draw me the curve of cos x. I'll check your answer, and I hope you do it correctly, because the transformation is very easy. I've just told you the steps as to how to approach it, And in the next video lecture, we will be discussing if we have a function fx, how will it transform to if I do this f of mod of x. I will explain you how the transformation will occur of this, and in the next video lecture, I will explain how 10x will transform to modulus of 10x and how 10 mod of x will get transformed. Okay. For now, thanks for watching the video. Thank you.